And every process can get acquire the number of other processes in the same MPI job, and you call this command. So next, they can get their rank. So the rank goes from 0 up to the one minus the number of processes minus 1. So this shows how you can have different processes doing different jobs within the same program. So here we have an if statement. So if your rank is not equal to 0, then you can carry out this statement. Basically, you can print out this message with your rank ID and the number of processes. But if you are ranked 0, then you can just print out this message. And this is the entire program. So you can see that we have MPI send here and MPI receive. So that's the essence of point-to-point communication in the MPI programming. So you can send the data from one process to the other processes. Okay, so we have went through a template of MPI program. Then let's go into the detail about how do you do point-to-point communication. So first, all the processes need to be in the same condition world to be able to send a message from one to the other. And all the processes are numbered by their rank. So it goes from 0 up to a non-negative integer. That's the number of processes in this communicator world. Then we will go over what information is needed for the sender to provide for this message passing, and what information needed from the receiver to receive a message. First, on the sending side, so just like in TCP, we need to know where's the data. So basically, this is a pointer in the memory address of the sending process. And how large data? So typically, you send a vector of something, so you can specify how many elements do you want to send, and what type of elements are you sending. It can be an integer or floating point or character. And also, sender needs to write the envelope for the message. The envelope will tell the MPI communicator who is the receiver and what is the tag ID of the message. So the reason why you need a tag ID is because this, the same receiver and sender can exchange multiple messages. So the tag ID allows you to differentiate between those different messages. And finally, the sender pushes the message for the network into the network for routing. And this is the syntax for MPI send. So first, you have a pointer to a memory buffer in the sender's memory. And then this specifies the number of elements. Notice this is not the number of bytes. So this is the number of elements in your array. And then this is the data type. It can be an integer or double point. So of course, all these different elements have different sizes per element. Then this integer specifies the destination, the rank of the destination process. And then you also have a tag, which is a non-negative integer. Then also you give this sending process a communicator. So the default is the MPI world. So here we mentioned that you have to tell the sending function what is the MPI data type. And this is a few predefined data types. You can send characters, so which is here, that's corresponding to this C-type data type. And then there are integers, so that's corresponding to signed integer. And then here's a floating point number that corresponding to the C-type here. And this is a double point. So you may ask, why do we just directly use a C data type? So the reason is MPI is a standard that can be applied to multiple languages. For example, Fortran and C++ also use the MPI data types. So by defining the MPI data types, all those languages can be more compatible with each other. So now on the receiving side, the receiver needs to know who is sending the message. So this is also identified by their rank and what's the tag ID of their message. Then also the receiver needs to know where to put this message. That means it needs to show the network memory address to save the data that's received. And then after the receiver specifies these two information, the network can just send a message to the receiver, and the receiver can go back to the computation. And this is the syntax for the receive command. So first, you give a pointer to point to the buffer that you want to store the message at. Then this is the size of the buffer. So actually this is the maximum number of elements. Let's say if you are receiving a message that has 10 elements in it, so you should give it a buffer that has at least 10 that have enough space to store these 10 elements. It can have 20 elements of space, but the other 9 pieces of elements will be just sitting unused. And then the receiver also wants to know what's the rank ID of the source of the message, and what's the tag ID of the message, then the communicator, and then the status. If you don't want to use this MPI status, you can just pass a constant called MPI status ignore. And then later we'll tell you how to use MPI status. Okay, so when you are trying to pass a message between two processes, the MPI will perform a message matching. That means this is the sender. Let's say the sender's rank is Q, and this is the receiver, and the receiver's rank is R. Then the sender needs to specify this destination to be R here, and the source needs to be Q. So basically these two has to be matched. Secondly, the sending type and receiving type also need to be matched. Basically you're sending integer, and the receiver is expecting an integer. Then this is the tag ID, also this needs to be the same, and the condition word, that's also be the same. So of course we also have the requirement for the buffer size. The receiver buffer size has to be greater or equal to the sending buffer size. Otherwise your message will have a buffer overflow. So if the MPI send and MPI receive matches all these criteria, then this message will be successfully passed from the sender to the receiver. Otherwise, this message passing will fail, and your program will crash. So if you look at this receiving command, so a receiver can actually get a message without knowing like what's the exact number of data in this message. You just know that it can have up to this number of messages elements, but it may be less than that. And also you can use a wildcard for the source. So for example, you can just pass MPI any source to the source here. Then that means this receive function will match to any sending function. Or you can also give this wildcard MPI any tag. That means no matter what's the tag in the sending side, it will match to this receive function. So on the sending side, you cannot use this wildcard. So you have to specify a specific sender and with a non-negative tag. And also both of them need to specify the communicator. So we have a default, that's MPI world. So now let's say you have this receive command. So you have called MPI receive, MPI any source. That means this message can come from any process. And then any tag, that means this message can have any value for the tag. And then that means after you receive this message, the receiver doesn't know who is the sender and what's the message tag and how many elements in this message. Then how do you solve this problem? How does the sender know that? So the trick is to use this MPI status here. So MPI status is basically a C structure. So first you declare that data type here. So you pass the pointer to that structure to this receive function. After the receive function returns, then you can use this command. So source equal to status.mpi source, and a tag equal to status.mpi tag. So this status is coming from here. So this is the MPI structure. That's all the elements it contains. It has the MPI status, source, MPI tag, and an MPI error. So in this way, you can still use receive message from any source and use any tag. But after you receive the message, you can still figure out what's the source and the tag. But the next question is how many elements? So as you can imagine, if I'm a receiver, I received an array of elements. I probably want to do a for loop over those elements. If my expected number of elements is less than what's received, then that means I will be looping over some invalid elements, right? So I definitely need to know how many elements are actually sent. So to do that, I can use this command, the MPI get count. So first you can declare an integer variable. Then you pass a pointer to that integer, to that variable, to this MPI get count command. Also, you also need to pass the status. The status variable comes from here. And after this function returns, it will populate, give you the correct count, the number of elements that you have received. And this is the actual number of elements that's contained in this message. And this is the syntax of the command. Then, so here I assume that you guys all know about C programming. So if you think about it, we need to provide a buffer, a pointer to an array in the memory that can hold all the elements. But then the question is, how do I know up to how many elements do I need to reserve the memory for? Let's say, if I'm expecting I'm getting like 1,000 integers, what if I received 2,000 integers? So if I just specify a very large number, like 1 million, then that means all of those reserved memory space will be wasted. So it'd be nice to be able to know how many elements that's in the message before I give you a pointer to store the message. To do that, you can use this command called an MPI probe. Essentially, MPI probe is to receive the envelope without actually receiving the content of the message. So the syntax is very similar to receive, except for the destination buffer. So first, the receiver can give the source rank ID, the tag ID, exclamation word, and also MPI status. So after the receiver calls this command and this command returns, you will get the status. So within the status, you can use MPI get count. So this will allow you to probe the size of the message before you actually call the receive. And this is actually called a dynamic receiving in MPI programming. So this is an example of the receiver. So first you create a structure called for the MPI status. Then you probe, let's say you want to receive a message from process 0. Then you probe the message with this command, and then you got this status. Then this is the number of integers that's in this message. Then you can call this MPI get count. So here is the number of the amount of number that's in the message. Then you call malloc. So this is you can reserve just enough buffer for the number of elements in this message here. Then this returns your pointer. So now once you have this pointer, then you can call MPI receive to actually receive the function. So now you can specify the exact number of elements that you have enough memory for. And also this rest is basically the same as before. So after you got the receive, you can print to some other computation on those data, then you can free that memory. So when you do C programming, always remember to free memory that you call malloc for, otherwise you have a memory leak. So this is how you can receive a message without knowing the exact number of elements in the message. Okay, so now we have went through all the components of this greeting for MPI program. Then we can read from the beginning to the end. So let me make sure. Okay, so here actually, since mobile, it will be very confusing for you to read this together at the same time. So I'll just read this as a multiple process. So let's imagine we have two processes created at the same time for this program. So if I'm actually, do I have a volunteer that can read this with me together? Do you want to try? Okay, so then I need to do a split personality. So let me say I'm the process 0 here. Then first I'm initializing the MPI world. So let me stand here. That's me as I'm process 0. And first I know I call this command and communication size that's 2. So right, I instantiated 2 processes. Then I get my rank is 0. So this is the same time if I have another process here, I'm going to be running the same command at the same time. I will get the same value for this count size, that's 2, but my rank will be 1. Right? So basically I have 2 processes running at the same time. So that means step on here. So let's say I'm the rank 0 process. I test this if statement. My rank is not equal to 0. That means I'll go in here. Then I'll print out a message. Basically that's saying greetings from process 0 of 2, right? Then after that, then you can see I need to receive messages. So here's a for loop. I know what there are two processes, right? This equals 2. Then I start from 1. So Q equal to 1 here. Then I receive, I give it a destination for this message, greetings. So essentially I'm reusing this, this reserved buffer here, greetings. And this is the destination for that message. And I know the maximum amount of character in the string, and it's an array of a character. And then my source is Q. So notice I'm looping through Q, from 1 to however number of the process in the process. And then the tag ID is 0 in the communicate world, and I ignore the status. So when I'm rank 0 process, basically I'll just stop here because I'm waiting for some message to be sent to me. And this is all the MPI receive is a blocking operation. That means I cannot move forward anymore. So let's rewind in time. So let's say I'm the process, rank 0 process. Then when I'm reading this if statement, that means I need to go into here. And this will create a string for you. So that's in this greetings string. And the content of that string is a greeting from process 1 of 2. Right, so this is my rank is 1 now. Then after I created this message, I call send. And this is the pointer to this string. And this is the length of the string. I need to add 1 because all the C string has special character, that's a /0 at the end. And the type of the array is a character. And also I know that all the other strings need to send the message to process 0. And I just designate a tag ID of 0. And also I use MPI counting world as the communicator. So here I'm sending a message. I'm process 0. And the process 0 here are expecting to receive. And you can see that these two need to be matched. Once they match, then the system will pass a message. So process 0 will receive the message sent from process 1 and print out the message. And for the process 1, after it sent the message, then also you can exit the if statement. The both of them can carry out this statement that's MPI finalize the return 0.
Yes. Where does MPI count world get its value at the 32,000?
Yeah, it's a default. So if you notice that you have lost this kind of all the uppercase characters, and also we looked at a few other examples like any source, any tag. So whenever you see this all uppercase string, that means it's constant. So everyone understand this process, right? Okay, so we'll be working on an exercise that's based on this. So you actually are supposed to write a code as a modification of this. Yes.
So the number of processes are 2. So, do you mean it is like sending and receiving?
So number of processes is 2, right?
Number of tasks.
So, okay, so the number of process 2, I suppose, they have a rank, right? So you have a rank, one process rank 0, the other one rank 1. Then you can just follow this command here. So what's your question?
And then we have 2 processes.
Right.
And then each processor has another 2 processes.
So can we be more precise? So processor means a physical device. So here, let's not worry about a physical device. Here we just have two processes, right? And you typically just assign one physical core per process, and those 2 physical cores may sit on different computer nodes that may be physically separated. So the other thing I want to remind you is that here I give you an example with 2 processes. But what if you have 3, right? So let's say I'm a rank 2. That means I also will go into here and I'll also be sending a message. That means they are both process 1 and 2 will both call MPI send. So we have 2 MPI send. So this is why in the process 0 we have a for loop here. You need to first receive the message from process 0. So we have this 1. First you start from 1, then goes to 2, right? So first you receive from process 1, then you receive from process 2. So this is a sequential process. Yes?
Do all of them emit and finalize at the same time, or that can be?
No, they don't need to be finalized at the same time. And this is the output. Let's say if you have one process, so just to remind you that this is your MPI program's binary. You don't actually declare ran this binary. You actually need to call MPI ran and pass the number of process to this record. Then this will be executed for you. If you have 4 processes, then you will have 4 different greeting messages. So one thing we probably want to do is to time how long it takes for your computation. So this is also a few problem or homework that you need to work on. To do that, you can use this command, MPI W time. So this stands for work clock time. That just means how many seconds has elapsed from some point in the past. And this returns a double. So let's say you want to time how long does process 0 used in some computation. So what you can do is to create 3 different variable double. Then if your rank is 0, you first call MPI W time. So this will return you double in the unit of seconds. Then you can run some computation. Then after this computation, if your rank is also still 0, then you call this command again. You have a finish time. Then you can just calculate the difference between start and finish. This is the amount of elapsed time, and you can print it out. So this is how you can time your computation. But remember, when you are running this, you are only timing the process 0. If you are process 1, you are not going to go into these 2 if statements. So you just still have a null value here. So we don't care about this. We're only going to print out this elapsed time with the process 0. So by now you have learned a few MPI commands. So you probably have some sense about the MPI convention. So first, all the MPI commands and variables start with this prefix MPI underscore. And then if they are all in the uppercase, then that means they are constant, like MPI convert or MPI any tag. But all the functions and types has just the first letter as in the uppercase, then all the remaining letters are lowercase. And also just to review that, so we are writing the MPI program in SPMD, so single program multiple data paradigm. So the same binary will be run in all these processes. So OS will be responsible for initializing all these processes on multiple computers. And then they will run in different type of data that's determined by their rank ID. Typically use process 0 as the master process. Basically that's responsible for receiving all the messages and finally printing out the results. And the other process are typically called worker processes. So the other thing I want to emphasize is when you read the code, you have to get a sense about if this communication is blocking or non-blocking. So this is how a blocking MPI send would work. Let's say you have process A that's sending message to process B. And first process A is carry out some computation here. So this y-axis is that's the time here. At this point, the process A called MPI send. But the same for the process B, it actually are running some other computations, so still hasn't called the MPI receive yet. So during this time, MPI will be blocked. That means it's just sitting here idle, waiting for B to hit that MPI receive command. After the process B hit that MPI receive command, then they are both are ready, so the message will be passed between them. And after that, the process A is safe to overwrite the message that's been sent, and the process B is safe to use the data that's been put into the pointer, buffer. So this is called blocking because the process A will not return until this MPI send has been finished. So the advantage of the blocking is easier to reason the code because for the receiving side, you know the receiving function is blocked. So after it returns, you can always save to use the data that's been put into the buffer that you designated. But the disadvantage is the CPU are basically idle when the message is being synchronized between the sender and the receiver. So alternatively, you can also use a non-blocking MPI send. So in that case, process A would call the MPI send in here. But then it actually will not wait for the process B to hit that MPI receive command. It can actually continue to the next statement. When the MPI, this process B hits that MPI receive function, then process A will actually deliver the message. Then after that, they can both continue. So it's a bit risky to remember that when the process A is in this segment of time, you cannot erase the data that's in the message. So that's the only thing you need to be careful. So the advantage is opposite of the other, the blocking send. So the advantage is that there's no blocking, no idle time. So for example, you can effectively use your CPU even during this time. But this advantage is your code will become more complex. So, for example, how do you know when is it safe for you to erase the memory that holds the message? So you have to call this MPI test to know that. So we talk about the two flavors for the MPI send. For the MPI receive, it's always blocking. So if you're a receiver, you can always assume that it has to be wait for the message to receive, then it continue. So this makes sense because typically when you receive some data, you want to operate on that data. So it should be better for you to wait for the message to receive. But exact behavior of the MPI send is implementation dependent. So typically behavior is that it's blocking for large messages. That means if you are sending 1 million integers, so typically the senders will sit there and wait until the message has been delivered before it returns. But for small messages like a few characters or a few integers, it's non-blocking. That means the process will return as soon as it hits this MPI send function. And of course, if you don't want this kind of guesswork, you can always use this explicit blocking or non-blocking version of the send and receive function. So those are not covered in this course, but you should know those options are available for you. And if you use just the MPI send and MPI receive, then this is a typical behavior. When you're writing MPI code, so it has much more way to hang and deadlock than serial code. So one typical behavior is if you're not careful and you don't have a match send and receive, the program will hang. So we talked about the criteria for match sending process and receive function, right? So the destination and the source and destination rank ID has to be matched. The tag ID has to be matched. Also the data type has to be matched. So, but if you use non-blocking alternatives, the deadlock is less likely. But it's your responsibility to test the failure of the communication. So you can use the MPI test to know if that message passing is completed or not. And also you can use MPI wait to wait until the message is passed and continue. Then also the standard specifies the order of the message that's being sent between two processes. So let's assume the process K wants to send two messages to process J. These two messages always will be received in the same order that they are sent. So let's say K sends A before B. J will always receive A before B. So this is called a non-overtaking principle. So it's always in a deterministic order. So let's say if you want to send an array of numbers from the first number to the last number from two processes, you can count on the MPI will guarantee the order of this array will be restored on the receiving side. So, but if you have two processes sending two different messages to the same process, even if you count the walk of time, if Q sends A earlier than T sends B, but it's not a guarantee that R will receive A before receiving B, because they are coming from two different processes. So this is not guaranteed. Okay, so let's go into this exercise in Canvas. So in this exercise, we basically want to ask you to provides GDU with a main function. So we can first go over this main function together. So first, this is a pretty standard MPI program. So you got a rank, and the P is the number of processes in this MPI job. So you have this convert. So let's declare a type here. Then also let's declare integer for the total of the number we want to sum. Then we initialize this MPI processes. We just assign this MPI converter to this communicator. Then similarly, we'll just get the number of processes in this MPI world, and also get my rank. And this is going to be something different. So let's say if you have 4 processes, we can call this random number generator. You can generate a random number that's based on your rank. And then let's calculate a number that's between 0 and 100. So basically we can just this probably need to be modified a little bit. So assume this is in here. So we model 100, so you get a number between 0 and 99. And all the process will print out the random number they have. Then everyone will call this command. It's called a global sum. So let's say you have 4 processes. These 4 processes will all generate 4 different numbers in here. And then we want this global sum function to calculate the total of those 4 numbers and return to this, assign to this sum. If the rank is 0, then we'll print out that the sum is however many, and then we can access the program. So basically your job is to implement this global sum function. So to give you a hint, so I'll show you the hello world program that we just went through in the class. So in this hello world, you can see that everyone has creates a message, right? If it's not rank 0, then they send the message to process 0, and process 0 print out or receive all this message one by one, and print out them one by one. So you can kind of make an analogy. In the question X side, everyone generates a random number. All the process can send their random number to process 0. Then process 0 can do the addition and print out the sum, right? So you can basically look at all the syntax here and then implement that global function right, in here. The key thing is to figure out the send and receive function. So I'll give you about 5 minutes to work on that problem. Yes.
We cannot access the C program. It says unauthorized.
It's written files.
Yeah. You go straight to the files.
Oh, okay.
It's in there.
Oh, okay. Okay.
I did the same thing.
Just direct the function global sum.
Sorry.
It's supposed to implement function global sum.
Yes, to implement global sum.
To note that this already teaches me. The random rank is the random number. So basically my int is
Is comp size, does that gets like the number of processes?
Yes.
comprises the number of what?
Processes?
So,
So look at the code here. So I want to turn this one number. You just use that one number. So just for one. So here you know the first thing and receiver node plus CD1.
so you said you want a number, but don't you have to say like the size of the number?
That's just a real size one.
Oh, okay.
Yeah, I mean, you can see how the value is right here. So I'm passing this
This
size.
is about the same. But not committed.
Yes, what's your question?
We need to modify names as well. That is
You can just use this name. So all you do is implement this global sum function.
okay. But then if the global sub function is correctly,
Not if
that
I
means
use
Yes. I mean, we have a bug here. It's random. Ignore this. So let's say you have a random
Is
number.
that the
that's a
current
sum.
sum?
There, no. That's the number that you're,
Because
that
I'm
they're calling.
okay.
So like if you're in the else statement, so if your rank is 0,
Mm-hmm.
then you start the sum at 0 and then sit and receive all of them,
Okay.
which is
should the other processes just return zero?
Yeah, that's a good question. They can return anything. I don't care. We don't care.
Because we never used it.
Yeah. Well, they don't get to print anything.
Oh, gosh.
Okay, so I think some of you already spent some time on this. So let's read the code together. So in this time, since we're doing parallel programming, let's do a small game. So I need you to pair with 3 other students next to you. So let's say we all have a team of 4 processes. Then, so let's then once you team up, assign a rank. Who is rank 0? Who is rank 1, 2, and 3? 4.
oh, so 4.
Okay.
So you're the 4th person. Are you guys the 3rd?
Okay.
Well, I can go with you guys then and be your 4th person.
Okay, then we pull it.
All right. So you all got the rank, right? So then remember your rank. Remember your rank. Then let's read the code together. So just focus on whatever you need to rank.
Okay, wait.
So first, let's say you already initialized
So
Then here, what's your P? Everyone's P is the same, right? 4,
They
right?
are three. They are three.
Everyone gets 4.
Oh.
Then now my rank, you all have a different ranks. Remember rank. So here, everyone is generating a random number at the same time. So can you generate a number? Okay, you all got a random number, right? So now, let's say you print out a random number, and remember we're doing parallel programming. You are all printing this message at the same time, right? So suppose you all have the same speed. So now let's go into the global sum. The parameters are the rank and the integer, that's the random number you generated. Then can you carry out this? If you are not rank 1, if you are not rank 0, then you call this command, right? So now if this is, let's say this is blocking. So you want to send, remember the number you want to send? But you cannot, you are waiting for rank 0. So rank 0 is here. So now I need you to tell this random number to. So rank 0 will first do what? So also rank 0, so I'll get a random number from rank 1. Okay, then rank 0 add, right? Then now the rank 0 receives the random from the second process. Okay, now from the third process. Okay, so now you all have that. So I need everyone to carry out this. So if you are a rank 0, you return your integer. But if you are rank 2, what do? You also return this, right? You just launch your number. So if you go back, you return from here. Rank 1 will print out something and finalize. But no one cares about the return from the other rank because this sum is not going anywhere. Any questions so far? So you guys are seeing that how busy this process 0 is, right? So basically if you are process 1, 2, 3, all you do is just send a message. Then you can return. The rank 0 has to receive sequentially one by one, then do the addition. Then return it, then print it out. So this you can probably answer your second question. So which step is parallelized and which step are serial?
The parallel are everybody within it.
I'm sorry?
The whole sum is parallel.
Yeah, okay. So first of all, let's say what's parallel. So you can see that everyone, if you are a process 1, 2, 0, 1, 2, 3, you are all carrying out this task, right? So the random number generation is parallel. It's generated at the same time. But now once you go into here, this is parallel. So the basically one process 0, need to do this for loop sequentially. It first receive message from the first process, then receive message from the second process. So this receive is a serial, and also this addition is serial, right? This is a non-blocking send, right? So you're sending a very small message. So that's parallel. Everyone just sends it and then returns. So this is the first question: which steps are parallel, which steps are serial? Basically, it's actually very taking a long time to do this. So we already answered this question. So is it non-blocking send or receive? All the MPI receive is blocking. So basically, when process 0 is here, it will just do one loop at a time. Can you use a non-blocking receive here? So this is all the MPI is receiving is blocking, but there is a non-blocking receive. Can you use non-blocking receive here? So remember, this receive will hit the function and it will return right away. So it's not blocking. So it's highly unlikely these two will be executed at the same time. So you will be getting you can return, but this you cannot be adding whatever the null value that's in the memory space. So typically non-blocking receive is very tricky to use. It's So but anyways, the receiving is blocking here. The sending, how about the MPI send is blocking or non-blocking? Non-blocking, right? So this is a very small message, and it's safe to return because you can just send it. Then this integer will be buffered by the network.
You said that small messages are non-blocking when they're sent, but what is the limit on what is considered a small message?
Very good question. So it's MPI implementation dependent. So actually, that's basically different for like OpenMPI, different from Intel. But unfortunately, this sending, blocking, non-blocking is a pretty not important for the programmer, for the developer. So you can, because you just need to pay attention, you don't overwrite that message you send right away. Okay, let's go over this question. How many additional receives are performed by process 0? How many? Right, -1, right? Do you think this would be slower or faster than a serial program? Yes, much slower. Because you are spending all your time to receive a message. But the only thing that's faster is when you try to generate a number. So what we're going to do next is to look at a program where calculating this number for each process will take a long time. And in that case, it makes sense to do the parallelization, right? Okay, so the other thing you have to remember is when you develop an MPI program, always try to kind of act as if you are multiple processes. So think in parallel. So you always think about how would the process 0 do in this kind of for loop? How would process 1 do? So how would the process 2 do? So that's all will be running concurrently. Any question about this program? Okay, so let's continue then. All right, so let's look at a non-trivial example of an MPI program. It's called a trapezoid rule. So you can, given a function fx, you can do an integration. So basically that's the basic area under the curve from a point A to point B. Of course, a lot of functions, you can have an analytical solution. For many other complex functions, you may not be able to derive this analytically. Alternatively, you can solve this problem numerically. That means you can use this trapezoid rule. So this is how you can approximate the integration results. Let's say you also want to integrate from A to B here. Then you just divide this interval into many small sections. And then let's say we look at the first section. This endpoint is here. You draw a vertical line here. Then it hits this point as a function. Then you can draw a trapezoid in here. And you can also calculate this trapezoid area by using a simple formula like this. So this is the first endpoint. This next endpoint, you can calculate the height of these two endpoints by calling this function f here. And also you would know the height of this trapezoid, that's h. And then you can calculate this one trapezoid using this formula. You just need to call the function twice, add them up, and then times the half of the width. And this is a approximation because you can see that this is a smooth curve, but if you divide it into 4 trapezoid, first trapezoid will underestimate the area of the curve. The second trapezoid also will underestimate, but the third one will overestimate, and the fourth one will always also overestimate the area of this curve. So to improve the accuracy, what you need to do is to divide this interval into a larger number of trapezoids. As the n increases, the approximation will become more accurate. But of course, the drawback is you're going to spend more computational time. Let's say you want to divide this into a million trapezoid. That means you need to evaluate this function f a million times. So that can be very expensive, and that can be a good candidate for parallelization. So how do we calculate that exactly? So this is the formula for calculating the area under the for one trapezoid here. Then let's say we want to integrate it from the endpoint A to endpoint B. Then this is the number of all the endpoints that you have. So x0 is A. Then h is basically the width of this interval divided by the number of trapezoid. This is the h. So the next interval is the next point is x1. That's A plus h. And the next one is A plus 2h, and etc. And the last one will be just a B. And then if you plug this number into this formula, and the sum of all this trapezoid, and then this will be the formula. So basically you have this h, that multiplies half of the first height, so that's this a here, then times x1, x2, until xi n minus 1. Then for last one, you also need to divide by 0. So basically that's how you can calculate with the mathematical formula. So now think about how do you implement that numerically. So first we have the two endpoints and the number of trapezoid. You can calculate the width of the trapezoid. And then you can first calculate the two endpoints, so FA and FB divided by 2. So that's the two terms in here. But then you can just use a for loop to calculate the terms inside from 1 to n minus 1. And first you can calculate xi, that's the a plus I times h. So basically that's what you are calculating here. And then you evaluate the function f at the xi, then add that to this approximation. That's you are doing all the terms in the middle. After you accumulate all this function across all the data endpoints, then you can just times h here. So that's basically this term here. So this is a serial code. Then how do you parallelize it? Can you see if you have 4 processes or 5 processes, how do you speed this calculation up?
Chunk them up into however many processes. Don't do it for each one, but split them up into like 5 different chunks if you have 5 processes.
Right.
And just kind of tell those processes the start and end.
Right.
Something
Yes.
like that, and then get back to something.
Yes. So basically that's the basic idea. So divide and conquer. So you divide that trapezoid into 4 large pieces. Each process can calculate their own section. So if you generalize it, so whenever you ask to think about how do you parallelize a serial program, so a lot of HPC programs talk about this faster methodology for parallelization. So basically you can think about 4 different steps. In the first step, you have a big problem in partitioning it into many basic tasks. So the goal is to divide the problem into many different basic tasks. Ideally, the number of basic tasks is larger than 10 times of the available processes you will want to use. After you have this number of basic processes, then you can figure out what are the communication that's needed between those basic tasks. The idea of course, these two need to be considered iteratively. A good design of the basic task is to minimize the amount of communication that's needed between them. So this will avoid the parallelization overhead. The other thing we need to think about is the dependency between different tasks. So that means if some tasks need to be complete before the other tasks, so those can also be very difficult to parallelize. So you want to minimize dependency among those tasks. So once you know the connection, the interdependency between tasks, then you can agglomerate them into composite tasks here. So the idea is to minimize, again, the dependency between these composite tasks and minimize communication between these composite tasks. And then after that, we can map those composite tasks into processes. So in our simple case, you can think about one composite task for one process. So this is called Foster's methodology: partition, communicate, agglomerate, and map. Then let's apply this methodology to our trapezoid problem. So here we have a problem that we need to calculate A to B here. Right? As we mentioned before, we want to partition this problem to many basic tasks. You can think about each trapezoid is a basic task. You can have a million trapezoid here. But then we can think about what's the communication that's needed between those basic tasks. It's very simple. Everyone calculate their area then they just need to calculate a sum across them. They don't need any other communication. Then let's agglomerate them into a composite task. So let's say you have millions of small trapezoids, but you only have 10 processes. What you can do is to combine the adjacent trapezoids into one composite task, and they can communicate within themselves. Then they can, after they have a partial sum, then they can just add them up to a global sum. So this is another way to explain that process. So this is, again, how you can calculate a trapezoid rule for this function. First thing is think about partition and communication. You partition this function to many, many trapezoids. The communication is very simple. You just need to calculate sum of all the trapezoid area. So next step is agglomerate and map. So in this case, let's suppose we have 3 processes. So let's agglomerate the adjacent trapezoid into one process, and we map to process 0. Then for the next one, the yellow trapezoid, also we agglomerate them to map them to process 1. And the blue one is mapped to process 2. Then we can do a global sum of all these areas. In these steps, there's no communication, so they are very parallelizable. But here we have a global sum that's a bit harder to parallelize. And then first, let's think about for each composite task, what do we do? So let's suppose you need to calculate your process 1, and you want to calculate this area. So you have 2 trapezoids to calculate here. And this is a function, so it's just called a trap, stand for trapezoid. You basically pass the 2 endpoints, left endpoints, right endpoints, that's these 2 endpoints here. Then also we can tell this function what's the number of trapezoid we have within this interval. So it will be 2 here. And then what's the length of the base here, that's the width of this 2 interval. And then we can implement a simple for loop. Since this will be carried out by one process, so that can be done serially. So this is the same function that you have saw before. So this is the function that we want to implement in here. So you have the half of the first and the last points. So this is your estimate. Then you loop through all the intermediate, all the terms in the middle. So you loop from 1 to number of trapezoid minus 1. Then every time you basically evaluate, calculate what's the x, that's the middle endpoint here. Then evaluate the function f at the x there. Then add that to the estimate. And then you times that estimate with the base length that's in here. You turn that estimate. Right, so basically this is how one process can calculate this one area. So now we need to parallelize it. This is blocked off, but you all know how to calculate. We all need to, all the process, let's say you start from 3 different processes. Then they all get their rank. So you may have a rank 0, 1, 2. And also everyone knows how many other processes are in your team. Also, let's calculate a few things. We have A here, that's A is x0. B is x6 here, that's B here. Then in total, we have 6 trapezoids, that's A equal to 6, 1, 2, 3, 4, 5, 6, that's in here. Then also you can calculate the width, h here, that's B minus A divided by N. So next we need to figure out how many trapezoids does each process need to calculate. So in total we have n trapezoids, and this common size stands for number of processes. Let's assume it's even divisible. So in this example we have 3 processes, and local n is equal to 2. Let's skip this first step first. So let's say you have process 0. You can call that function with your local a, that's this endpoint, to local b, that's this endpoint. And then you can get an area back. So this is process 0. Then similarly, if you are process 1, then you need to change your local a and local b, right? If you process 1, the local a needs to be here, the local b needs to be here. Also, you can calculate the yellow area by process 1. So remember, this is a parallelized section, right? So in the exercise that you have done before, all the process just generate a simple random number. But in this calculation. All the processes actually are doing something meaningful. They all assign a section of the function to calculate, and they calculate the integration results. So then after all, they have calculated the integration results. And this is also the command that you are very familiar with now. So you have implemented how do you calculate global sum. So basically, if this process is not process 0, then they just send their calculation results to process 0. And you are basically sending one double. So this is a double, then just one number. But if you are a process 0, then you first keep track of what's the local integration results then assign that to the total integration. Then you ask for the result from every other process. You start from 1, then you look through the end result. So first you ask process 1, what's your results? You receive that, then you accumulate that to the total area. Then you go to process 2, then receive the result, then you accumulate it to the total. So now this is finished. Got a question?
Is there a good way to not have to wait on each process individually in turn?
Yes, that's a very good question. So that's our next exercise. So
Cool.
there's a better way to do that. But the key point to remember is this is just one last step. If you are evaluating a non-trivial function, the function evaluation is very expensive. This function you can think of this is a very, very expensive function. And this process is parallelized. So now, when you try to develop a program, so the trick here is how do you compute local A and local B. So I will give you a few minutes to think about it. This is all the variable you have. So let's think about you can pick a rank. If you are rank 1, you know what's the area you need to calculate to go from here to here. Then how do you calculate it? You know the width, and you know how many trapezoid. But then what's your local A and local B? So let's all think for a few minutes. So this is the essence of the single program multiple data. So each process will figure out, based on the rank, what's the region you need to be responsible for. I've got some answers here. Okay, so
your local A would be local n times rank, and then your local B would be local A plus local n times h.
right, very close. So you just need to offset by this A here. So you have a global A here, right? So you offset it a bit. Right, so basically the local A is basically you have A, that's your starting point. The rank, if you are rank, then times how many trapezoid has been taken care of by whatever that's before you. If you are a rank 0, then this would be 0, so you start from A. And then this number of a width you have to go over, so you start from whatever that's beginning, then how you go by h, this local n number of trapezoids. But if you are rank 1, so this will be 1 here, you know you should start from here. Right? So basically, the key thing is to use your rank to figure out what is the task that you need to work on. So once you figure out the local A and local B, then you can just pass it to the function here. Then this should be a good parallelized program to do the integration. Okay, any question about this program? So remember, this is the second parallel program you have worked on. So the only difference is we are actually doing something non-trivial here. So we are calculating the area and then add them up. So in the parallel programs, also we talk about local variables and global variables. So this is different from local variables and global variables when you're talking about Java programming. So you're just talking about a local to a function or local to a class. So here we are talking about local to a process. So global variable means this content is common across all the processes. Basically, everyone declares same variables. Do they have the same value for those variables? If they have the same value, then those variables are global variables. If that content is distinct for each different processes, it's called a local variable. Typically, local variables are different because they are a function of my rank. Because that's when you have all the processes started, that's the only difference between those two, between all these processes. Or if they are a function of other local variables, if the other local variables can itself be a function of my rank. So this is the second method. You can have a local variable. Or this message is received based on my rank. For example, if I'm rank 1, I may receive a different message from the rank 2 processes. So all this can be local variables. So now let's do this exercise together. So you have this program to calculate the trapezoids, and all this is a variable that you have used. Which one of them are local variables, and which one are global variables? Yes. How about local n? Is local n a local variable? So why?
No.
Is it? Is it? So is the local n a local variable or a global variable? Right, so local n is actually just a way to tell us this, in this process we have this many trapezoids to calculate. It's actually the same value between all these processes. So you can tell from the names, local A and local B are all local, because the local A is a function of my rank, and the local B is a function of local A, so that's also a local variable. So these numbers all will have different values for different processes. But how about this total integration area? Is this local or global?
It's still a local.
Yes. Why is that?
Because it's only within process 0. Like, yeah, I mean it exists, but it only ever gets a value within process 0, so it's still local.
Right, right. So this is the third category. So this is the message received based on my rank. So this variable, the total is defined with this value, and that's based on this message. I mean, the other process will also have a value for total integer, but it's just not getting updated, and it's not being printed out or passed to anything. Okay, let's work on the next exercise. So we still have a few minutes. So this one will be much harder. So, I mean, this will be useful for you to think about in T-models of 4. So as we mentioned in the previous implementation, the process 0 basically did everything. So remember the global sum, the process 0 received those messages and they performed all the addition. So let's think about another global sum function that uses a tree structure to distribute the message passing in addition to multiple processes. To make this simpler, you can do it, it's not that hard. So to make this easier, let's consider the number of processes to be the power of 2. So let's suppose you have 2 processes or 8 processes. So this is the reason why it will be faster. So this is what you have implemented before. So let's say you have process 0, 1, 2, 3. What you have done before is the process 0 needs to be receive function from process 1, then do addition. Then now it goes to receive function, receive that message from the process 2, then do addition, then receive this. So you can see this is all addition, right? The complexity is basically goes linearly with the number of processes. If the A is the time you spend on the receiving addition, so this is all done sequentially with A times N. Now here is the magic of parallelization. What you can do is this. You have 4 different processes. So process 2 can send a message to process 0, and process 3 to receive that, do the addition. But the key thing is to do the same thing for the other process. Process 3 sends a message to process 1, then process 1 do the addition. So now at this point, process 2 has a sum of these 2 processes, right? And then process 0, 1 has a sum of these 2 processes. And then process 1 can send the results to process 0, and process 0 does an addition. So the reason why it's faster is the process 1 is working in parallel as process 0. So in this way, you can reduce the number of the additions and received by log 2 of n. This is the reason. The key is that you're having other process are doing the same work as process 0. So now you have to implement this. So also remind you that this is whatever we implemented before. So you can use the same program function interface, basically you will get the same input here. But rather than just sending and receive function from the same partners, the partner need to be changed. So just a hint, so you have obviously have a for loop here. Because you have, if you have n process here, you need to do the n log 2 n number of send and receive function. So that need to be in a for loop. The partner need to be changed every time you go to another level. So this is a pretty difficult one. So what we'll do is you can spend the next few minutes to work on this. The next lecture will start from this exercise. If you cover the rest of the
Different because in here, sending and receiving is the same.
the number of
That's a good question.
And what is
Source and destination.
I know anything about
N?
processing.
Yeah. What is A?
Yes,
A
true.
is the time it takes to do the add and receive.
Oh, okay, so calculating the time. Okay, okay. So,
Yes. Yes.
the partner
Yes.
No, that's not the process. The process is
right.
Like this.
We're gonna use this equation.
Yes, yes. Yes, yes.
That's sort of a tree. It's, I mean, it says like use a tree structure. But there's a equation. I know it's long. Your children, it's how if you have a tree as a like a list, and then you get your children.
So you should
That.
have left child of left child is I plus 1, 2I plus 1. And your right child is 7, I
Two,
plus
yes.
2.
Okay, 2 on. So that's kind of how we do this, right? Find your partner.
So the partner is what is the partner? The partner is the child of
It's who you're sending your stuff to.
So the partner
So
is
it'd be your parent.
So your parent is
Divide.
Get the
That's what I
parent.
was trying to work out.
No, let me just find it. Try to find the parent.
So to give you some hope, the program is not very long. It's just this much. So
Wait, is that
it's very
it?
simple
Where
program.
is it? Where is this?
That's all.
Power of 2 I.
Easier is
Wait, log of. Oh, it's just.
that's it.
Partner is the ceiling of the floor.
Thanks. Look, it's the floor of something. It's the floor
So if I'm the first one, aren't my children the 2 after?
of something. Well, you know the problem?
So I'm at 1. My partner
but not necessarily. So you could have 1, 2, 3, and each child as a children of 2,
Right. Okay, so this is one.
yeah, this is the
These are his children.
and this is the
These are those
So
children.
the concept,
So this guy's child is here, which is 0, 1, 2. So how do we get from 3 to 5? 2 minus 1?
minus 1, the floor minus 1
No, that doesn't work.
makes load tree in an array.
You know they have a T.
I just use it in an
What?
has a tree structure. Yeah, it's index minus 1. You don't have like you take the floor bit. Yeah, just take the floor bit.
So 0, this guy is 0 minus 1. Okay, that's 0, 2 minus 0. Oh, to get the parent.
You got a parent.
Oh, I was talking about going. Yeah. Okay, so what is it? 4
I don't know how you just do that.
4 of 10 minus 1 over 2. It has to be a 4.
You wrote floor. You meant floor, right?